Okay, let me just start sharing my screen. And this is sort of an unusual occasion for me because I just finished teaching this stuff this week. So just half an hour ago. So it will be like repeating myself, and I will assume that you get bored, but really you shouldn't because this is many people here are new, except some of you. So how's everyone doing? Everybody's happy? I can see Gökberk. How are you, Gökberk? Can you speak?
I'm doing fine. How are you doing?
Very good, because we have also checked this way whether your voice comes to everyone else, so you will be able to ask questions very clearly. Why Seymour decides to talk about cellular automata rather than 2D materials? Okay, it's a very hard question for me, but I thought that this would be a lot of fun, and I don't get to do it. I don't get to present this stuff because usually people expect from me to talk about 2D materials and DFT calculations, etc. I thought PI seminar is a very good occasion to also talk about this stuff that we did. Okay, this is this is San Sebastian, where I did my postdoc. Imagine doing a postdoc somewhere here. You would be tempted to think about deep questions like what is life, kind of stuff. And I have read these three, I mean, two of them are books. The third one, it has a video version of it also. There's a book of the same talk by Bernstein. And in his talk, he talks about, he says that his lecture will be giving in an interdisciplinary fashion, where he will talk about mainly music while doing quixotic forays into fields like including physics. So I'm doing the reverse. I'm doing 2D materials, but I did a quixotic foray to this field, and I am deeply passionate about this field, and I want to share that passion with you. Okay, so anyone who is interested, these are the books to read. And then there is this map. I also saw this map while I was in San Sebastian, and it really connected for me to many things that I was interested in, but I never made this kind of a map to see that all of them actually come together. And eventually I will talk about our paper where we actually cite these people. These red ones are the ones that we cite. And these are really big names like von Neumann, Stephen Wolfram, John Conway, Chris Langton, Per Bak, Stuart Kaufman, etc. This is the so-called complexity science, and basically to get into the head of these people, you should definitely start reading by reading this paper. This is a hand waving to Professor Ilday. His group is named Simply Complex, and they really implement this way of thinking in their research. And that's mainly what they do, but this is really a side work for me, unfortunately. Anyways, let's read this if it's okay with you. Is it okay with you? The elegant body of mathematical theory pertaining to linear systems like Fourier analysis or orthogonal function, etc., has successful applications to many fundamental linear problems in physical sciences, and they tend to dominate even the moderately advanced university courses in mathematics and theoretical physics. The mathematical intuition so developed ill-equips the students to confront the bizarre behavior exhibited by the simplest of discrete nonlinear systems like this equation. If you don't know this equation, it started as a model of population growth and decay, but it shows it's a very simple version of chaos. So it's very simple model, as you can see, just one variable iterated over and over, but it produces something unprecedented. I would therefore urge that people be introduced to, say, this equation. Now I'm introducing you to this if you are not introduced yet. Early in their mathematical education, this equation can be studied phenomenologically by iterating it on a calculator or even by hand. Its study does not involve as much conceptual sophistication as does elementary calculus. Such study would greatly enrich the students' intuition about nonlinear systems, not only in research, but also in the everyday world of politics and economics. We would all be better off if more people realize that simple nonlinear systems do not necessarily possess simple dynamical properties. Good. Okay, so this is the so-called logistic map, and we will come back to logistics later on. Let me just, yes. So cellular automata really starts with John von Neumann. What he wanted to do, he wanted to build a self-replicating machine. And this is the outcome. Basically, he thought about grids, and every grid can have a certain states, okay? And there are rules that change those values in those grids accordingly. This is in particular a 29-state automaton. So it can have 0, 1, 2, 3, up to 28. And as you can see, it basically replicates itself. While von Neumann was thinking about it, he, let me say, accidentally discovered all the intricacies of DNA replication and translation while DNA was not there. Like, he was logically thinking about how a machine would self-replicate and discovered many fundamentals of real biological systems. But let me give you a simpler version of self-replication on cellular automata. Here it is. It was developed by Langton. And you can see that there are these grids, and these colors represent states. And when you run this system, it basically takes an arm, comes back to itself, and basically, sorry, I will just pin my video here. Yes. Basically, it self-replicates. Good. One example of cellular automaton. And let me continue. Here's an article that appeared at the cover of Nature. Basically, they looked at a living lizard. This is a living lizard, and it has these scales on top of its skin, and apparently it changes over time. And they discovered that using numerical simulations, mathematical derivations, we identify how a discrete von Neumann cellular automaton emerges from a continuous Turing reaction diffusion system. Some of you probably know very well Turing reaction diffusion system, but my point here is that cellular automaton can be present in real life, okay? Very clear example of it. Here's another application of cellular automata. I'm trying to sell this idea to you right now, and you are aware of it, right? I hope I'm doing a good job. So it's, for example, Wolfram went to these people, or they went to him, I don't know. But he basically stimulated interest in cellular automata as a possible new approach to turbulence phenomena. And they first developed this very simple model, again, a cellular automaton, which did very good. But then it was developed further and ended up being this lattice-Boltzmann method. Let me show you the results of this lattice-Boltzmann method. Do you see? It's a pretty good approximation of fluid flow. Good. So living systems, fluid flow, and it keeps going on like this. This is another Nature cover from 1984. Here, Stephen Wolfram basically looks. Who is Stephen Wolfram? He is the creator of Mathematica that probably some of you have used. Why he created Mathematica? Because he wanted to study this kind of systems. He basically think of Mathematica as a telescope, while Galileo was looking for planets and discovering our real universe, exploring it. He says that Mathematica is my telescope and I'm exploring the computational universe. Sure, Wolfram Alpha, and then there's a language, Wolfram language, many very unique stuff. Mathematica by itself is a very unique programming language, which is basically symbolic. So you can just take a square of a pigeon and it will give you something reasonable. Well, probably not, but if you are going to take a square of a pigeon, you should first try it in Mathematica to see whether it gives you a result or not. Anyways, Wolfram discovered that this is an empirical study, so he cannot clearly tell you when chaos starts and when life starts, but basically he realized that these cellular automata, if you run them, they either go to homogeneous state. You see, this is not just some photocopy accident. This is photocopy accident. This is not. You start with a few states and it basically disappears because of the rule. Basically, the rule is too nihilistic and it just dies out. This one settles into a periodic motion. So spatially homogeneous states, sequence of simple stable orbits, chaotic aperiodic structure like this, or lifelike structure. Like you can tell a story of this. There was someone who met someone else and they married and they had some children, etc. Like it's lifelike. Do you see my point or his point? Yes. Let me give you some examples of simple elementary cellular automata. These are the rules, and basically it is called rule 30 because of the binary version of this one. So if you change this binary to decimal, you will get 30. This is really quite amazing, and basically you can have 256 different rules, and when it came to rule 30, Wolfram discovered this rule and he was amazed by it. He took it to Richard Feynman, saying that it creates something that I cannot decode. It's sort of computationally irreducible. Feynman thought that he can easily crack it, but couldn't. What is it? It's basically a rule. So for example, if you want to find what will happen to this cell, you basically look at this cells, 0, 1, 0, go find 0, 1, 0, 0, 1, 0 is here. And then you decide what will happen to that cell. It becomes 1. What is interesting is that it produces this pattern that has chaos and order together somehow. And this middle line passes through all the pseudo-randomness tests. So basically, Wolfram actually used this rule 30 to generate random numbers in Mathematica for 25 years until he found a better way. We will come back to cellular automata, this automata. That's why I'm spending too much time on this one in particular. Is it boring so far? Any questions? No? There's a $30,000 prize if you can figure out what this cell will be with something that is faster than running the algorithm itself. Okay, standing prize. Maybe rule 30 would be enough for Wolfram, but he discovered something even more amazing with rule 110. When you run this rule, this is rule 110, and we have an animation here showing how it runs. Basically, you can see that you look at here 0, 0, 0, then it should be 0. You basically decide what will happen next accordingly. Is it clear? This one is clear, right? What comes out is fascinating. Look at this really, again, you can tell a story. There was someone who met someone else, then they interacted, then turned into something else, etc. And Rule 110 was shown to be Turing complete. So basically, it means that anything computable can be computed using Rule 110. Okay. This was a very important proof, and basically there was some controversy about it appearing before this book appeared, and it was a problem, but never mind those rumors, etc. Basically, Stephen Wolfram wrote a book that is like this thick, a new kind of science, and in the beginning of that book he says that he compares his Mathematica to Galileo's what was it? Telescope. Thank you. And this is Rule 110. I'm still trying to sell you Cellular Automata. So Cellular Automata was used by Gerard 't Hooft, who is a Nobel Prize winning physics Nobel Prize winning scientist, who is not very happy with the current Copenhagen interpretation of quantum mechanics, and he came up with this cellular automaton interpretation of quantum mechanics, which is not perfectly complete. It doesn't solve all the problems, but it's worthwhile reading. Then going back to Wolfram, he actually wants to derive all the physics starting from cellular automata. There is this Wolfram physics project talking about space and matter are emergent features of hypergraphs, etc. Okay, good. Cellular automata is important, right? Now let's talk about Conway's game of life. We lost Conway to COVID-19, unfortunately. He was a Princeton mathematician, and back in his youth, he came up with this particular game. He called it a zero-player game. So basically, you have rules. Again, you have a grid, and you have rules. The rules are the following. So the state of this one is decided by the sum of these states. If the sum is fewer than 2, it basically dies out. If it's exactly 2, it stays as it is. It's more than 3, it dies again. And if it's exactly 3, if it's dead, it becomes alive. Basically, we call them decay, stability, and growth, these 3 particular rules. Okay. And if you run this rule, it gives you nice patterns. Well, it acts lifelike. It has propagators and things like that. People went crazy about Game of Life and did very nice architectures. They did, of course, a Turing machine, first thing that comes to your mind. But let me show you one that I really like. Are you ready? So watch the beginning very carefully, and then it will make sense at the end. This is a highly curated initial state of Game of Life, and it's being run. It will be worthwhile waiting, you know. There's a surprise reveal. Boom. It is simulating itself with itself. Do you see? At the top. Since it's a Turing machine, it can calculate itself as well. Good. Besides this kind of playing with this stuff. There are serious papers that were published in serious journals that look at the dynamics and physical properties, especially the criticality of game of life. Because, you know, when you look at it, it's sort of between the order and chaos. So people were wondering whether it's, for example, self-organized critical or not. For example, Bach published a paper in Nature discussing this stuff. Okay, we wanted to do a serious paper on this as well. Now I will start talking about what we did. So basically, how much time do I have in total? 50 minutes. Okay. Is it boring, Hocam, so far? No. Okay. So basically, Conway's game of life takes one, for example, if it's decay, 1 goes to 0, 0 goes to 0. If it's growth, then 0 goes to 1, 1 goes to 1. Stability, it stays the same. What we did is we represented it in a difference equation way. So for example, let's check decay. 1 goes to 0, 0 goes to 0. What is delta S? So if the state is 0 and delta S is minus S, so minus S is also 0. So the change is 0, 0 goes to 0. If it's 1, then delta S is minus 1, 1 minus 1 goes to 0. So we can express Conway's game of life in this difference version. What we did is just to put lambda in front of it, a tuning parameter. What we were looking after is somehow managing the rate of change. We didn't want it to go right from 0 to 1 or 1 to 0, maybe visit some parts in between. Now, hence, we can have any number in between 0 and 1, okay? So that makes the intervals also continuous. It can go from 0 to 8. So what we did is we started defining this summation ranges, operation ranges in between. So for example, this is decay. Then after 1.5, it's stability. After 2.5, it's growth. After 3.5, it's decay again. So now it becomes continuous cellular automaton. Okay, are you following? Is it boring? No. Look, if you take this uniform state and just apply stability to it, it becomes this kind of a uniform state. If you apply growth to it, it shrinks up to here. If decay, it shrinks down to here. Now let's apply the same thing one more time, and you get this kind of a fractal, right? Self-similar structure. If you really do it, if you really do the mathematics of it, you eventually get into something called the Cantor set. I hope you have heard of it. Just start with uniform distribution. And for example, you have 0 here. And if you apply growth, it will go to lambda. And lambda we define as G operating on 0. If you apply G again, it goes to 1 minus lambda squared, etc. It's a lambda dependent Cantor set. Now, don't forget about this, okay? Because we will use this lambda dependent Cantor set a lot. So 0th order is just 0 and 1. The first order depends on lambda. The second order, the new states appear to be lambda squared, and the third order is lambda cubed, etc. So 14th order Cantor set has a polynomial of lambda to the 14. Good. Now, let's start with lambda equals to 1 and change lambda, decrease lambda. As you can see, it first looks quite like game of life, but then there are 3 different states that are fighting with each other for the region. There are these stripes, there are these zeros that appear blue, and then there are flickers that appear in between, more on the turquoise range. Do you see now we come back to lambda equals to 1 and 0 again prevails the system, okay? Now let's look at this system. What happened?
May I ask something before going a little bit further?
Okay.
Yeah, is there something conserved here? Is there any condition that applies to all of them?
Very good question. So that was the point of Perbach as well. People were saying that, okay, you will get self-organized criticality usually in many systems that have conserved quantities. So in principle, no, game of life is dissipative, nothing is conserved. Is that a clear answer? Are you satisfied or?
Oh, yes, okay. Then I will have another question towards the end.
Yes, okay. Okay, thank you very much. So when you look at the density, and eventually it settles into a certain density. So let's look at the density while we change the lambda parameter. So you can see that until you reach some critical lambda, it remains the same. It looks also very similar to game of life. Then suddenly it starts increasing the density, and then there are these other phase. So there are lots of phase transitions going on here. Let's analyze them in detail. So let's start with this phase transition over here, which is the main phase transition. So if you are over here, closer to the game of life side, then you end up having an inactive asymptotic state, meaning that if you run 1,000 by 1,000 system for 10 to the 5 time steps, it definitely stops the activity. And there are 28 different runs here. They are just averaged out to a single, but they usually stop at the same point. However, even ever slightly change to lambda towards the other edge ends up being in an active asymptotic state. I wouldn't claim that we understood everything about it, but at least we have defined it. We have quantified that this is there. It needs to be understood. But why at this particular lambda? Let me explain that. Now, if you look at, for example, let's imagine this kind of a state. You have S in the middle, but these are zeros, and these are the states that were just born yesterday. So that's why they are lambda. They are not lambda squared something, etc. So the summation will be 4 lambda, okay? And when 4 lambda is above T3, it goes to decay. When it's below T3, it goes to growth. So there is an operation change when lambda is equal to 3.5 divided by 4, which corresponds to this 0.875. And this is basically counting the number of sums in the actual system. That is, so this kind of situation apparently appears quite frequently. That's why even a slight change in the fate of the system leads it to active or inactive asymptotic state. If you look at the other transitions, let's look at, for example, these transitions. And when you see a phase transition, you usually want to analyze it in a close by neighborhood, in a log-log scale, right? And if it's classical, stochastic phase transitions, you expect some kind of a slope that corresponds to some sort of a universality. Well, we have a slope, but we also have these bumps. And we figured out that those bumps are coming from the higher order terms of Cantor set. So if you just take 3 lambda equals to T2, that is the main transition. But there are these micro transitions that are in a close by vicinity that can be found by just solving this equation, 14th order equation. But that solution coincides with the jumps. But in terms of the slope, we have no idea what this slope tells us, and that's not being quantified yet. Now let's talk about this gliders. If you remember, there were these things that were propagating in the game of life. While you are changing lambda, they are actually adapting to that lambda change until some point. Let's run it again. You have a glider that is propagating, but as you change lambda, it changes color, but it still propagates until you hit this magic number where it dies out. So we wanted to understand why this happens. And basically, we had to recreate this in depth. So look at this. For example, this cell, it has 3 live neighbors, right? So it's going to grow. So in the next step, it becomes G times 0, okay? And you continue applying rules like that, and you can see that all these values, G0, G0, GG0, GG0, appears G0, G0, GG0, GG0, just shifted. So it basically shifts the structure. That's how it propagates. But why it stops? Now, for each cell, you can imagine its neighborhood sum. So for example, for this cell, the fate depends on the sum of these cells. These cells in respect depend on lambda. For example, this one depends on lambda with a 4th degree polynomial. So if you sum this one, and this one, you get a 4th degree polynomial in lambda. If you plot all these polynomials, you see that right at the point where lambda is this critical value, where it dies, you have again a transition from decay to stability. So you break the loop. And to figure out that value of lambda, we had to solve 11th order polynomial, which we did using Mathematica, by the way, very easily. Now I want to talk about another organism that we discovered here that is not present in the original Conway's game of life. So let's start with original game of life, Conway's game of life, with this particular initial condition, and it goes to something boring like this, a flicker. Now let's start with the same initial condition, but now I am at the range lambda equals 0.8384, and you get a propagator. It's a period 36 propagator. And the nice thing about this propagator is that it is not engineered. It is autocatalytic. It emerges out of these rules, and it can live only in a certain region of lambda. So lambda has to be larger than lambda A or smaller than lambda R for this thing to be alive. And since it looks like Rayfish, we called it Rayfish. And this is a very nice example of autocatalysis, right? Because, for example, these red arrows, these transitions are actually present in the original game of life. What lambda-dependent game of life brings us is that it creates also these loops so that you get an autocatalytic loop. And why this Rayfish is so abundant, I will show that it is abundant in a moment with actually running MATLAB live. You will see it emerge. Because some of its stages are very simple. For example, you can start from this, as I've shown you just before, and it basically builds itself like transformers and starts having these bigger shapes. And while it is swimming, it also visits very simple stages. So this paradox of being very complex and abundant, like us, human beings are very complex, but they are abundant. Why? Because they start from very simple initial conditions. Okay. Okay, demonstration. It's demo time. It's MATLAB time. Let me change color map to Parula, because otherwise you can get hurt. Okay, so what I will do is I will run game of life starting from initial condition that is 0 everywhere, but randomness in the middle. let's see what I get. So for example, let's start with game of life, which is lambda equals to 1. I hope you are not bored yet. No? Okay, let's run it. Yes. Problems with live action. Okay, I started from very simple initial condition in the middle, and what happened? It spit out these propagators. Let's do it again so that you see a different initial condition. It spits out a propagator. Do you see the propagators going? Yes. Now, if I go to lambda 0.85, okay, maybe I can decrease this so that you can see it more clearly. Do you see it still spits out these gliders, right? But if I go to 0.84, which is the region where Rayfish also can live, it will spit out Rayfish, as you can see going. These are the diagonal ones are the gliders, and the horizontal or vertical ones are the Rayfish. I have periodic binding condition. Let me run it again. Do you see Rayfish? Yes. There is a question, I guess. No. There isn't a question. Okay. If I go down to 0.83, there will be no longer Rayfish because it's not autocatalytic in that regime. Okay. It can still, what do you mean by the system can grow, but it will not spit out Rayfish. It should spit out also the glider, but it didn't. Let's run again. Yes, glider is. They coincide each other and then they can grow. They can grow. They can also cancel each other out. So it's also another life of cake. Like yeah. They kill each other. Yes. Definitely. No. It's deterministic. Everything is deterministic. Like when they meet each other, it's still deterministic. Like you can arrange meeting head-on collision will always give the same result. This will always give the same result. So there's like the optimum angle that they meet each other. Can they reproduce Rayfish? Yes, I think so. I hope so. I believe so. Should we try? Just two Rayfish meet each other. Okay, this is turning into my course, you know, where we just have fun with the. Should I do it? I can do it, but it could be boring for some people. Shall we do it? Many people want me to do it. Let's do it. So I will put. Let's do it. But as a result, I will not tell you some of the other results. So. Okay. This is what happens when you have experimentalists, right? They want to experiment. Okay, so I will try. If it doesn't work, I will just quit. 0, 1, 1, 1, 0, 0, 1. Let me see if this will create a Rayfish or not at first. No, it will be hard. Hocam. Let's do, oh, okay, because of lambda, okay. Let's go with lambda. Okay, it's hard. Let's do it later. We already lost an audience. Okay, Rayfish and other fish. There are many fish if you go beyond lambda equals to 1. I've never spoke about lambda equals to larger than lambda equals to 1 because you know, the initial idea was to slow the system down, but higher lambda makes it oscillatory. And basically, I have the note here for the students, crazy, when you go lambda above. So let's start with 1.3. And I can do this, I can do this, it will be very quick, so watch it. It produces these self-replicators in a global scale. Okay, did you see those self-replicators? Depending on lambda, for example, if you go to 1.4, it's yet another regime. 1.5, yet another regime which has a lot of fish. Let's do it again, but let's have a lot of randomness so that we have a lot of fish together. Do you see the fish swimming? And they are interacting, and sometimes they cancel each other, sometimes they create more fish. And let's finally look at 1.6. It's propagator replicator, so it propagates but also replicates, so that it produces all kinds of very interesting stuff. I mean, we can sit here all night and make it 1.59, 1.58, 1.57. Everything is explorable, beautiful, and awesome. Good. Any? Yes. The meaning, for example, could be that your computer needs an input 1 and 1, a logical gate that takes 1 and 1 to 0. So you can use them as logic gates. 1 and 1 comes, but it produces 0. Does it make sense? But you can have all kinds of other meanings too. So it's very easy to just lose yourself and attach a lot of meaning to this kind of models, which I tend to do, but it's also dangerous. Like you have to stop yourself at some point. Good. I have only 6 minutes left, so I will go very quickly after this point. So we started applying this lambda idea to other automaton as well. For example, rule 90 is one of them. Sorry that this appears here. I can put it here. So rule 90 is just another rule that depends on the sum of the outer cells. And basically in the rule 90, if you start the rule 90, it first creates Sierpinski triangle, okay? But as I'm running it, I'm also changing lambda. So as you can see, you can get all kinds of different regimes as you change lambda. And we can explain those regimes by looking at the sums and again, these parabolas depending on the lambda, and we can explain why there is this transition, why there is this transition, and why there are other transitions. This one is in particular interesting because it's not because of the Cantor set, but because of basically having growth, then decay again. So you basically get stripes, start getting stripes, because look at this. Before, this one takes growth. If you apply growth to this point, it will take you here. But you are in the decay regime, so you cannot get here. But if you are in this regime, you can go growth, and you are in the growth regime, you can go growth, and then you are in the decay regime, and it brings you back. So it forms an autocatalytic loop that produces period 3 stripes. So period 3 stripes is a very good, apparently very good environment for other fun stuff to happen around it. So basically what we did is we applied some filtering so that period 3 stripes appear like blue background. And here what we are showing you is that while you are changing lambda, you can actually get from chaotic behavior to lifelike behavior smoothly. You can smoothly change lambda, and you can go from chaos to life and back to chaos. And this is, here's an example of taking it too far in terms of interpretation. there is this thing that lives until this point where it becomes something else. So we have, for example, connected it somehow vaguely to punctuated equilibrium ideas, where some evolutionary species, after a certain tiny changes happen, they turn into something totally different, depending on the evolutionary pressure they are underneath. Okay, this is an email from Stephen Wolfram saying that your paper looks nice, and many other stuff. Then we continued with these ideas. In particular, I wanted to show you this. 3 minutes left. So basically, we went back and we wanted to implement logistic extension to all possible elementary rules. To be able to do that, we had to sort of rewrite the ideas of elementary cellular automata. Basically, elementary cellular automata are named by the numbers, the binary to decimal numbers, right? But we started naming them in terms of these operators like decay, stability, oscillation, and growth. So we have 4 operators, and normal binary rules are like 8 bits. So you have 2 to the 8, which is 256. In our case, we have 4 bits, but 4 operators. 4 to the 4 is also 256. As a result of this definition, we had decoupled the elementary cellular automata into 2 sets of operators, asymmetric operators and symmetric operators. And as a result, we were able to produce this beautiful periodic table of elementary cellular automata. All the unique rules are here, and as you can see, the chaotic ones are clustered together, sort of clustered. And the regular ones, the similar patterns appears in a similar regime, etc. But this definition made it possible to produce logistic elementary cellular automata, where, for example, we were able to produce lifelike structures even in the rules that are boring in the original version of elementary cellular automata. Okay. And then we figured out a general way of approaching this lifelike. Since we have this parameter that you can change to achieve lifelike structure, we claimed that lifelike structures can be thought of as starting from chaos, and then within the chaos, you have these periodic structures appearing. And while you change the parameter, those periodic parts become more and more favorable. And then they basically squeeze down the chaotic parts and produce these very complex propagators. These are basically chaos being tamed into order, okay? As a result, you get something that has order in it, chaos in it, and some meaning, okay? Lifelike meaning. There are lots and lots to uncover in this, but I will stop here. Thank you. Any questions? Okay, no. Any questions? Yes, please. I didn't. Oh, yes, yes. So the question is very good. How do I calculate the entropy of the patterns? I didn't, but I did something else. I would be really happy to show you. So, and we are currently working on it. So let me show it to you. That was the last slide. Demonstration, edge of chaos in logistic ECA. So basically, this is an image here. And you can see the complicated parts need a lot of bit cost to represent in a PNG file format. So what we did is we basically put all the logistic rules, okay, into a folder. So let me go to Dropbox, Seminar, Logistic Elementary Cellular Automata. Okay, look at this. Rule 0, 0.5, rule 0, 0.6, rule 0, 0.56, etc. Right? Now, then, these are all PNG. Then what I do is I basically sort them with respect to their size. So the initial ones are the chaotic rules. Do you see? Initial ones are the chaotic rules. But as you go down to the edge of chaos, you will find a lot of more lifelike rules. You know, for example, this one looks lifelike. This one looks lifelike. Do you see? So that's a very important aspect of this this kind of studies. You have to come up with a clear way of finding entropy and mutual information in this kind of systems. They will take you towards the edge of chaos, but it's always elusive. Do you know that word? Like you feel like you are almost about to solve this mystery, but then you can't, because, for example, here there are several rules that looks chaotic to my eye, but apparently somehow PNG can make it very small file. Then I guess my human eyes are mistaken. There are a lot more order here than I can see. Do you see my point? Yes, that's a very important question which I answered. Okay. Okay, good. Any other questions? Any questions from Zoom audience? No, they are bored. They are bored to death.
I have several questions. So, I don't know which one to ask. I think
You can ask all of them. No, sorry.
So, this is a dissipative system.
Yes.
And somehow there is some sort of energy in the system. And that energy is used up by the rules.
Okay, when you say energy, there is something conservative going on, or isn't it?
So there is something that governs this action, right? So I call it energy, but
Okay, okay. You mean like if we were to produce this in actual world, we would want an energy to run this system. Yes, I understand.
yes.
Okay.
So to make an analogy with the real thing. So in every step, actually, you have an energy cost. So to take that step, to take the next step, there is an energy cost associated.
Good.
So my point is, when you
Can I use these ideas in my next article? Very nice ideas. Yes.
But when you run the system, actually, yes. I feel like you start with a certain amount of energy to begin with.
Yes.
And then your system uses that energy.
Yes.
And then this comes to my mind, then how come you have continuously running systems?
Okay, because they are open systems in principle. So those energies that you use up, you get from somewhere.
In the form of, let's say, zeros. So the empty regions of space goes back to the original energy state that it has.
Yes. Let's see. So
then my point is, so that's why it said
no.
I
It's
can't put it into words, but I think that's
generally when I present this, physicists say energy, entropy, something like that. So I should really, not me, everyone should really take into account those kind of stuff. And put some sort of physicality to it.
Yes.
And the route to that is define some sort of energy. I agree. The other question?
Well, no, it was like, so is there a way to set up, your lambda is a very good control parameter.
Oh, yeah.
That's my feeling.
I see.
And is there any other rules that you
It could be like a parameter that is connecting it to the energy bath.
Yes.
So very nice. We are going somewhere.
Yes. And then The next thing is, let's say you create artificial boundaries rather than a rectangular
Sure.
thing. You create boundaries in this thing
Yes.
and confine your system and see how it responds. Would it give you another tuning parameter for the rules?
Maybe.
Rather than having a periodic boundary condition, let's say you have ones
Oh yeah,
at the
I see.
corners.
I
So
see.
this will
I think there are studies like that, but we didn't do that. But
So I'm thinking about how to simulate actual phase transitions with something like this.
thank you.
I think that there will be a tuning parameter. One
No.
tuning parameter.
You know, the interesting thing is this is deterministic phase transition. So it's not stochastic. But if we start defining lambda as some sort of stochasticity with the bath, then it will probably go towards actual phase transitions. Yes.
Any other questions?
Yes.
In your previous talk, the previous semester, you mentioned something like the ideal lambda for a line closure, so-called line.
In the previous talk, what talk?
Beginning of the semester, the previous semester, you were giving a conference here.
I don't remember, but okay. Bilimsel iletişim topluluğu. Okay. Sorry. Yes. Oh yeah. I remember that. Now I remember. So you are referring to Langton's lambda. It's completely different. Langton's lambda is basically looking at many different rules. And from those different rules, he is basically looking at the probability of producing ones. If it's 0.5, it means that equal probability of producing zeros or ones. Around that region, you have this edge of chaos kind of stuff. While here, we have the same system, same set of rules, but we are changing a single parameter continuously. You cannot change lambda continuously in Langton's version. Here, you can change it continuously. That's another important difference. Thank you very much. Any other questions? Sorry, any other?
Okay. No.
No. Thank you very much. Thank you very much.
Thank you, Seymour.
Thank you very much. Take care.